Hello everyone. Today's lecture is going to be on the topic of the Inclusion-Exclusion Principle. And this Inclusion-Exclusion Principle is a counting principle. It's used to help people count certain things. Like a lot of maths problems, at least part of them, the combinatorial ones would be count the number of ways to do this, or count how many of something there is. And sometimes counting it is not easy, but sometimes it's easier. You should probably have watched the intro to counting video from the 2019 December camp first before watching this one. Because I'm going to assume a bunch of stuff from there. I'm also going to assume that you know what factorials are. So those are like n factorial, which is 1 times 2 up until n, multiplying all the numbers until n, and more the combinatorial significance, that's the number of permutations of n objects. Okay, so what is the inclusion-exclusion principle? Well, one way to understand the inclusion-exclusion principle is from small cases. So let's say I have two sets. I have a set A and I have a set B. And I want to know if I take the union A union B, I want to know how many elements are in that union. I'm also going to assume that you know the set notation like union and intersection. So the one that looks kind of like a U, that's union. That's the set containing all elements in both of the smaller sets. And the other one is intersection. That's the set containing what is in both of the two sets. So for example, A would be the set on the left, and B would be the set on the right. Now there is a little part where they overlap, and that is A intersection B. That's the part where they overlap. Whereas the union would be, let me just draw some red over here. The union would be what's inside both sets. Now, if these sets don't overlap, if they don't have anything in common, then I could just say the number of elements in the union would be the number of elements in the one set plus the number of elements in the other set. That's if they don't overlap. But if they do overlap, if you look at the diagram, we're adding the set, the number of elements in set A plus the number of elements in set B, and we're counting the middle part twice. So we need to subtract how many elements are in the intersection of A and B. Okay, and this is the inclusion-exclusion principle for two sets. Okay, I'll also do the one for three sets now. There's a set A, a set B, and a set C. And I want to know how many elements are in the union of all three of these? A union B union C. Well, as before, I can say, okay, let's take the number of elements in A plus the number of elements in B plus the number of elements in C. Then, of course, I'm counting the overlap between A and B twice. So I need to subtract the overlap between A and B and subtract the overlap between B and C and subtract the overlap between C and A. Now, are we done? Well, if you look at the part in the middle, it was included in the A, adding the number of elements in A and in B and in C. So it was included 3 times, but it was subtracted 3 times when I took away the number of elements in A and B, the number of elements in B and C, and the number of elements in C and A. So currently, this expression I have on the right hand side does not include this piece in the middle. So I need to add it back again. So that's the number of elements in A, intersection B, intersection C. So that's what is in all 3 of those sets. So from this example, you should be able to see more clearly how the inclusion-exclusion formula works. If I want to know how many elements there are in the union of 2 or 3 or more sets, I first add together all the cases of just one set at a time, and then I subtract all the cases of 2 sets at a time, and then I add together again the intersection of 3 sets at a time. So it goes plus, minus, until you get to the intersection of all of whatever number of sets you have. And that starts from 1 set at a time, then minus taking 2 sets at a time, so you have to take all combinations of 2 sets at a time, then plus all combinations of 3 sets at a time, and so on. So we can write this formula in a more general case, or in a more general way, if we have n sets. So we have A1, A2 up until AN, and we want to know how many elements are in the union of all of these AIs. A1 union, A2 union up until AN. So that would be adding together all the sizes of the individual sets, then minus the sizes of all the intersections of 2 sets at a time, plus sizes of all 3 at a time. If you know sigma notation, I can write it as follows. This would be the sum from, let's say, j equals 1 to n, negative 1 to the j minus 1 times, let's see, the sum. So j is the number of sets we're taking at a time. So this goes from 1, 2, 3 up until n, and then we're summing over all combinations of j number of subsets at a time. So we're looking for all subsets big J of the set of indices 1 to n, where the number of elements in big J is small j. And here I have the intersection of all the elements, all the elements of J AI. Okay, if you don't know sigma notation, it's a good thing to learn at some point. But if you do know it, see if you can understand this formula that I wrote over here. Another different way to write it is as follows. I'm just going to sum over all subsets of the number of elements from 1 to n, as long as the subset J is not the empty set. And I take the cardinality and intersecting of the elements in J of that particular set. Okay, so that's like official formula for the inclusion-exclusion principle. But generally, if you like to work things algebraically, just like formulas and stuff, then you can remember this formula with the sigma notation over here. Most of the time, combinatorially speaking, it's better to think of adding sets one at a time, then subtracting intersections of sets two at a time, then adding intersections of sets three at a time, and so on up until you have all your sets done. Okay, now we're going to do a few examples of seeing the inclusion-exclusion principle in practice. So why would you do inclusion-exclusion principle? You want to count the number of things. Generally, you would do it when counting this sort of, if you want to count the intersection of a certain number of sets at a time, if you can, sorry, not that one, these intersections, if you can count each of these intersections over here easily, each of the individual terms, if you can do those easily, but it's hard to do the left-hand union of all of them, then it's probably a good time to use inclusion-exclusion principle. Okay, so here's an example. We are going to count, see how many integers, let's see, integers between 1 and 2020 inclusive are divisible by 2, 3, or 5. So they have to either be divisible by 2, or by 3, or by 5, or possibly 2 and 3, or 3 and 5, or 2 and 5, or possibly even all three of them. So the sets that you have in this case is A is the set of all integers divisible by 2. B is the set of those which are divisible by 3. And C is the same thing with 5. And what they're asking for is how many elements are in the union of these three. Okay, so according to the inclusion-exclusion formula, this would be the number of elements in A plus B plus C, and then subtract intersections of 2 at a time. Sorry, that's a vertical line, and then add together all three of them. Okay, so A, how many elements between 1 and 2020 are divisible by 2? Well, that's going to be half of them, so that's 1010, plus how many of them are divisible by 3? So that's going to be 2020 over 3, but because it's not divisible by 2020 is not divisible by 3, we're going to have to take the floor of this. And then divisible by 5. Since 2020 is divisible by 5, this is just 2020 divided by 5, which is 404. Minus, now we want to know how many are divisible by 2 and 3. That's what the intersection means. Most of the time intersection means and, so it satisfies both properties. So how many are divisible by 2 and 3? Well, that just means divisible by 6, because 2 and 3 are relatively prime. So that would be 2020 over 6. And floor that, since 2020 is not divisible by 6. Then B and C, that would be 3 and 5. Again, because they're relatively prime, that's the same as 2020 over 15 floored. And then minus 5 and 2, that just means divisible by 10. So that's 202. And then plus, how many are divisible by 2, 3, and 5? Those are all mutually relatively prime. So that just becomes 2020 over 30. Say 1010 plus 2020 over 3, that would be 673, I believe, unless I've made a mistake, might be, plus 404 minus 2020 over 6 would be 336. 2020 over 15 will be 134, I think, minus 202, then plus 2020 over 30, that will be 67. And then you get your final answer. I don't feel like working it out right now. You can do that yourself. Okay, so that's an example of using inclusion-exclusion principle. Let's do another one. I think I'm going to need a new page here. How do I add a new page? Hold on, just figuring out how to add another page here. There we go. That's probably it. There we go. Okay, another classic example of inclusion-exclusion principle, there'll be this one and then there'll be another example I'll do afterwards, is called derangements. You might have heard of derangements before. Now I'm going to show you how to get the formula for the number of derangements. Okay, so what is a derangement? A derangement is a permutation of, let's say, n elements where no element is in its original place. So, for example, we have n people and they move around, uh, they swap places, they can just move around as much as they can. Let's say they're on a circle, n people in a circle, or they have seats around a table and they move around and no person is at the seat that they were originally at. And each permutation like that is called a derangement. And the question is, how many derangements are there? Okay, so here there's a slight tweak to the inclusion-exclusion formula that we'll need, because the previous inclusion-exclusion formula tells us the size of a union of a number of sets. Let's go. If we go back to the previous page, all of these tells us the size of a union of two or more sets. What we need now is the intersection of the complements of those sets. Or if you look at a different way, we have n elements, right? So we can have n sets, a1 up to an, where ai, for instance, is the set of permutations where the ith element is in its original place. So the key word here is we're looking at when the element is in its original place, not where it's not in its original place. Now, if we define the sets AI in this way, and we look at the union, A1 union A2 up until the union with AN, what will this set represent? Not the number yet, we're just looking for the set itself. This set would be, as I said before, intersection is sort of like and, union is sort of like or. So the union of all of these is where the permutations where the first element is in its original place, or the second element is in its original place, or the third element is in its original place up until the nth element. So the union would be the set of permutations where at least one of the elements is in its original place. Now you might look at this union and say, but that's not what we want. We want all the permutations where none of the elements are in its original place. But the good thing is that this is completely opposite to what we want. And that's a good thing, because the permutations where no element is in its original place is just all the permutations minus those where at least one of the elements is in its original place. I'll say that again. The permutations where no element is in its original place. So what we actually want, I'll just write that as a question mark, is equal to all permutations minus this union that we have over here. A2 union up until AN. Now the good thing is we know the number of permutations. So this number, mystery number that we're looking for, the number of all permutations of n elements is just n factorial. And then we're just taking minus the size of this union that we have over here. Okay, so that's n factorial minus, and then we have this big sum, and hopefully each of those individual terms is easy to write down. So first, we're adding together the sets one at a time. Of course, the minus changes all the addings to minuses and minuses to pluses. So one at a time, all subtracted. And then we're adding together all the intersections of all combinations of 2 at a time. I'm not going to write all of those down. And then, let's see. Then we're going to do minus 3 at a time, and so on. Now, that's n factorial. Now the first one is, what is A1? A1 is the number of permutations where the first element is in its original place. So the other elements are literally free to permute any way they want to. So A1 is just n minus 1 factorial, because it's the same as the number of permutations of the other n minus 1 elements. So A1 is n minus 1 factorial. A2 is also n minus 1 factorial, because the second element stays in its place and the other n minus 1 are free to permute any way they want to. The same for A3 up until AN. Each of these is n minus 1 factorial. And there are n of these, so this is n minus 1 factorial times n. Now the next term, we're adding together all combinations of 2 at a time. So A1 intersection A2, remember intersection is similar to AND. So we're looking where the first element stays in its place and the second element stays in its place. The other elements are free to permute any way they want to. So there are n minus 2 factorial ways for the other n minus 2 elements to behave themselves. They can permute any way they want to. And this n minus 2 factorial is the same for any two pairs. So if it's A1 and A4, I want element 1 and element 4 to stay where they are, and the rest of them can permute any way they want to. So each of these individual terms is the same, n minus 2 factorial. So the question is, how many terms do we have? Well, how many pairs of 2 elements are there from n elements? Well, that's n choose 2. And of course, you know the formula for n choose 2 in terms of factorials. The same pattern continues for 3 elements at a time. It's n minus 3 factorial times n choose 3. And then pluses and minuses alternate in that way. And the last term would then be plus negative 1 to the n minus n factorial times n choose n. Okay, I'm going to replace each of these factorials. I'm going to write it slightly differently. You'll see why I'm writing it in this way. So n factorial minus, and this one I'm going to keep as n factorial, and then I'm plussing here n minus 2. Actually, let's rather keep it as n minus 1 factorial. That's n minus 1 factorial times this n I'm going to write as n factorial over n minus 1 factorial times 1 factorial. And this other one, this n choose 2, I'm going to write out in terms of factorials. So that's n factorial n minus 2 factorial times 2 factorial. And then minus n minus 3 factorial. Again, I'm going to write the factorial out, the binomial coefficient in terms of factorials. So that's going to be n factorial over n minus 3 factorial times 3 factorial, and so on. As you can see, all the n minus something factorials get cancelled out with the denominators. And I'm going to write it in this way. N factorial over 0 factorial. You should know 0 factorial is equal to 1. Minus n factorial over 1 factorial plus n factorial over 2 factorial minus n factorial over 3 factorial, and so on. Of course, there's a common factor of n over here. So n factorial. So I could write this as n factorial times the sum of 1 over, the alternating sum of 1 over each of these factorials. 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and so on. All the way up until plus negative 1 to the n 1 over n factorial. And that is the formula for the number of derangements. For those of you who know about this magic number e, this is very close to n factorial over e. Cool. And there we are, that's the number of derangements. You can write this big sum inside the brackets over here. We can write it in sigma notation as well, but I'm not going to do that. And the last, like classical case of using inclusion-exclusion principle is to get the formula for the Euler phi function. So you should know Euler phi function phi of n is equal to the number of positive integers which are less than or equal to n, which are relatively prime to n. And this Euler phi function, if you don't, well, now you're going to learn it. There's a formula for the Euler phi function, which is the product over all, let's do n first. N multiplied by the product over all primes, which are factors of n. So all the prime factors of n, and for each prime factor I'm going to multiply by 1 minus 1 over p. And if you multiply this big product out, of course you can see it as n times 1 minus 1 over p1, 1 minus 1 over p2, times 1 minus 1 over pk, if k is the number of prime factors of n. If you multiply this big product out, you'll get a formula which is actually the same as what you would get if you use inclusion-exclusion principle to calculate this Euler, oopsie, that's not how you spell Euler, Euler phi function. So this I'm going to leave as homework. Use the inclusion-exclusion principle to calculate the formula for the Euler phi function. Good.